Hi, my name is Zixian. In this talk, I'm going to tell you some surprising results of hardware transaction memory we found, and I'm going to challenge what we thought we knew about caches. This was joint work with Steve Blackman at ANU and Mike Bond at Ohio State. The story all began in 2020 when I was an undergrad student at ANU working on my final project. My advisors discussed this cool new GC algorithm with me that uses hardware transaction memory. The design looks clean, and we think it's going to perform well. So I did some readings on transaction memory, and also the relevant menu to know how to program HTM. After that, I thought I knew enough about HTM. I wrote some toy programs, and everything seems to be working fine. So I started implementing this cool new algorithm. Instead of seeing our cool new algorithm in action, the only thing we got was constant aborts of transactions due to capacity reasons. Just to be clear, we knew capacity abort is a thing. What confused the hell out of us is that the capacity limits should not apply in our cases, because our transactions are far smaller than the capacity limit that we think it is. At this stage, I'm getting more and more nervous. My final project could be ruined. So I decided to read through every single paper I can find about HTM capacity. To my surprise, published results can differ by orders of magnitude. Here are two papers. One shows a capacity of 7.5 MB, which is roughly the same size as the LLC, while another found the capacity to be a mere 26 KB, which is roughly the same size as the L1 cache. Both of them use the exact same CPU. What? I couldn't believe this. And it's not just two papers. Many published results differ wildly. Turns out, I thought I knew how HTM works and I knew how caches works, but I was wrong. In this talk, I'm going to unravel this mystery. I hope, after this talk, when you are in the same position as I was, you can avoid making the same mistake and save yourselves a lot of time. Now, before I get into the answer, I have to briefly explain some background information. You have probably heard of transactions before, especially database transactions. Transactions provide atomicity to, for example, database operations. One of the biggest advantages of using transactions over logs is that they support composition. If you call into a library that uses logs, you have to know the details of the logs to avoid deadlocks or data races. Transactional memory makes the semantics of transactions available to program execution and provides atomicity to a sequence of instructions. Inside the transactions, you can perform memory reads and memory writes. You can even do different computations. The memory read in a transaction is referred to as a read set, and the memory written to in a transaction is referred to as the write set. These two sets are used for conflict detection. Hardware transactional memory, or HTM, is an implementation of transactional memory where hardware structures and logic are used to keep track of read and write sets and to detect conflicts. HTM has many different applications. The atomicity guarantee can naturally be used to implement concurrent data structures, such as concurrent trees and concurrent maps, replacing lock-protected critical sections. It has many other use cases. For example, HTM can be used for security reasons, such as protecting against cytochannel attacks, or detecting data races in programs. And people have been even trying to build concurrent garbage collectors using HTM. However, there is one important limitation of HTM we need to be careful about before we build any application on top of it. That is, HTM has finite capacity. Transactions can abort due to conflict, which is expected, but more surprisingly, transactions can also abort for exceeding hardware capacity. This is the case if you look at commodity HTM, such as Intel TSX. This is because that the hardware structures required to track unbounded read and write sets are impractical. Let's talk a bit more details on what we mean by capacity. When we say read or write capacity, we mean the maximum number of distinct memory reads or writes that can happen inside a transaction. We use the methodology introduced by Richardson and Barnes, as illustrated by this figure from that paper. For example, to measure the read capacity, we start by constructing transactions that sequentially read contiguous memory of increasing sizes. We can then draw curves showing the fraction of transactions that commit or abort for different reasons, for different sizes. Now we can focus on the curve showing the fraction of transactions that actually commit, and the height here indicates the success rate. We can then read from the curve that the maximum possible size is 26 kilobytes before transactions always abort, and that is the read capacity. So, why should I care about HTM capacity? Importantly, it affects the design of programs that use HTM. If you know that your transactions are always going to abort, maybe you want to find an alternative. When we measure the size of a transaction by the number of distinct memory accesses, we can get a sense of how likely it is going to abort. For small transactions, such as inserting elements into a list, or atomic copying of few fields of an object, they are not affected. However, for large transactions, which is required for use cases like side-channel attack mitigation, or copying multiple objects and updating their references, the transaction could abort due to a capacity limit. Given the importance of HTM capacity, why isn't there a definitive number for HTM capacity and the condition under which a capacity abort will be triggered? The main reason is that hardware vendors do not publish this information. This is because that the implementation is a trade secret, and so that they have the flexibility to change the implementation details when needed. As a result, people have been trying to measure HTM capacity. The capacity of Intel TSX has been widely studied as it has been widely available since 2013. Prior work agrees that the write capacity is tied to the L1 size. Our finding is consistent with the prior work, so we won't discuss it further. However, the story is very different when it comes to the read capacity. As shown before, many published results differ wildly. Broadly, the read capacity findings in published work can roughly be divided into three categories: L1 size, half of LLC size, and LLC size. How can published results differ by orders of magnitude? Now, with the background information out of the way, I'm going to unravel this mystery. The key idea that will be used throughout the talk is that cache eviction causes aborts of transactions. We normally view cache behavior through a performance lens, where evictions are fine because we care mostly about the hit-miss ratio. However, we need a very different mindset when it comes to HTM. HTM uses cache invalidation to detect conflicts. Therefore, if a transactional cache line leaves its LLC, it cannot be tracked for conflicts anymore and will cause an immediate abort. Any eviction could be devastating if an expensive transaction is speculatively executed. Avoiding eviction is the key to large HTM capacity. In the remaining part of the talk, let's take a deeper look at two anomalies in prior work. For each anomaly, I'm going to show a key element of modern cache design that gives the surprising result. Then I will show different strategies that mitigate these unwanted surprises and increase the capacity. Finally, I will use this surprising cache behavior to reconcile apparent contradictions in prior work. The first anomaly we are going to show is that Reason and Barnes reported read capacity roughly as big as L1, while others show read capacity proportional to the LLC size. Here is a quick reminder of how the read capacity is measured by Reason and Barnes. First, a chunk of contiguous memory is allocated. Then the benchmark attempts multiple transactions of the same size, with each transaction using a different part of the memory. Each transaction sequentially reads contiguous memory. Finally, the benchmark explores a range of different sizes and records the fraction of transactions committing for each size. By running the micro-benchmark released by Reason and Barnes on the same CPU as they used, we are able to reproduce the L1 capacity results they had. We also ran the micro-benchmark on other microarchitectures and observed similar results. This is really strange. Remember, LLC eviction leads to aborts. Specifically, eviction at any of the LOC sets is sufficient to cause an abort. So why do we observe L1 size capacity? That is, why do we get an LOC eviction of a transactional line after only roughly L1 reads? How is that possible? To understand this, we need a deeper understanding of how caches work. To start, let's look at a simple example of a direct map cache. Assuming the cache has 32 lines, when we sequentially access some contiguous piece of memory, the cache lines will be loaded into the cache. Now the cache line is filled with some pre-existing data, shown in blue. What will happen if we have a transaction accessing 33 lines? For the first 32 cache line accesses, the pre-existing lines in blue get evicted, and our transactional lines are loaded into the cache. So far so good. However, when we access the 33rd line, there is a cache miss and we have to evict the rightmost line in the cache because the cache is direct mapped. The evicted line is in the transaction reset, causing the transaction to abort. So the read capacity is roughly the cache size. Now, what if we have a set associative cache with an LRU replacement policy? Again, when we sequentially read some contiguous memory, the cache will be filled, and the cache lines are distributed among the cache sets. With the cache filled with pre-existing data in blue, again, let's see what will happen when executing a transaction of 33 lines. When we access contiguous memory in a transaction, the least recently used blue lines are evicted, and the transactional lines fill in the cache in the same fashion. When we access the 33rd line, we have to evict the least recently used line in the rightmost set, which is a line in the transactional reset, aborting the transaction. As before, the read capacity is roughly the cache size. The LOC is LRU, right? But if so, L1 size capacity is impossible. But what if I tell you that LOC is MRU? That is, most recently used lines get evicted. No way, right? Wouldn't this result in terrible performance? Turns out, modern caches do have elements of MRU, and there's good reason for that. It is to mitigate cache thrashing from streaming workloads, where it doesn't make sense to keep those cache lines around because they will never be used again. So, how would the cache behave with MRU? As before, we have a cache full of existing data in blue. When we start a transaction, instead of evicting the least recently used blue lines, which are at the bottom, the cache evicts the most recently used blue lines, which are at the top. This is fine so far. Until the transaction accesses one more line, it evicts the most recently used line in the rightmost set, which is part of the transaction. This causes an immediate abort of the transaction. In this case, the read capacity is much smaller than the cache size. The situation is even worse on real CPUs because the wait size on actual hardware is much greater than 4. We have just seen that MRU with a full cache is problematic, but what if we start with an empty cache? The situation is now much better because no eviction is required during the transaction, and we will get read capacity roughly the same as the cache size. Similarly, if you start with a cache already warmed up, like the one here already populated with cache lines to be accessed inside a transaction, again, no eviction is required either. Just like when we start with an empty cache, we can get read capacity roughly the same as the cache size. So, having an empty or pre-populated cache is great for transactions with large read set. But how do we create cache states like this? The first strategy is invalidation. That is, before starting a transaction, we use a privilege instruction to invalidate all levels of caches. Another strategy is warm-up. That is, before starting a transaction, we warm up the cache with lines to be accessed in the transaction by repeatedly read that piece of memory outside of the transaction. These two operations are completely opposite in terms of cache effects, yet in our experiments they achieve roughly the same read capacity. With invalidation, it achieves 0.87 LOC size capacity, while warm-ups achieve a slightly larger 0.93 LOC size capacity. The results are very surprising. However, if you think about the cause of L1 size capacity, that is MRU, you will see why this is expected. Because invalidation corresponds to the scenario of starting with an empty cache, while warm-up corresponds to the scenario with pre-populated cache. So, how does this help us reconcile the wildly different results in prior work? Turns out, if you read the papers carefully, publications that achieve read capacity proportional to LOC size actually use different methodologies than Ritz and Barnes. Instead of using different memory for different transactions of the same size, this work reused the memory, which effectively warmed up the cache. In fact, we were able to quantify the effects of reusing memory. Each curve here shows how the fraction of committing transactions changes with the number of reuses. The darker the curve is, the more the reuses are. As you can see, the more you reuse, the larger the read capacity gets, until it converges to roughly 0.76 LOC size. To summarize, the cache state and the cache replacement policy dictate what to evict upon a cache miss. As a result, if transactional lines are not already in the cache, and if the MRU replacement policy is used, transactional lines will be evicted before accessing full LOC capacity. The second anomaly we are going to show is that some published results show roughly LOC size read capacity, while others show only half of LOC size read capacity. In fact, curiously, in our own experiment, we sometimes see half of LOC size read capacity despite using warm-up or invalidation. But after rebooting the machine, we can see LOC size read capacity again. This is really strange. You might wonder, wait a second, I thought you just told us that we should get LOC size capacity if we use warm-up or invalidation, even if MRU is used. So what's going on? To understand this, we need to revisit our experimental methodology. The contiguous memory we allocated for transactions is in fact only virtually contiguous. On a machine with fragmented physical memory, the OS is likely to give us random physical pages to back our allocation request. How can this affect HTM capacity? If you have random physical pages, certain cache sets will be more heavily used. As a result, it takes less time before a green line gets evicted. In fact, a theoretical result due to GoNet tells us that we can expect the effective capacity to be about half of the actual capacity for completely random pages. To address this problem, we enable huge page support in the OS. When we request virtually contiguous memory backed by huge pages, we are guaranteed that it is physically contiguous as well. We use the reuse results as example, as huge pages show the most profound effects in this scenario. As before, we have reuse without huge pages, achieving about 0.76 LOC size read capacity. On the right, we have reuse with huge pages. As you can see, huge pages allow transactions to access nearly the full LOC capacity instead of half of LOC. We conjecture that prior work that achieved LOC size capacity instead of half LOC size could be running with contiguous or nearly contiguous physical memory because of the state of the operating system and the machine. To summarize, since LOC is physically indexed, if an application is allocated with random physical pages, certain heavily used cache sets will be full before others. This leads to the eviction of transactional lines before accessing full LOC capacity. Now that the read capacity is no longer a mystery, what can we do about this? For programmers that use HTM, we suggest warming up the cache before transactions. It is important to note that this is not to speed up the transaction, but rather to enable transactions to commit and avoid expensive aborts. Using huge pages is another simple and yet powerful technique to ensure consistently large capacity. Invalidating cache is only recommended in some cases due to its huge performance penalty. For architects designing and implementing HTM-aware cache replacement policy could be adopted to avoid evicting transactional lines where possible. To conclude, in this work, we found that HTM read capacity is limited by effective LOC capacity, which is in turn linked to the replacement policy and physical indexing of LOC. As a result, different cache status can result in orders of magnitude less capacity. This helps us reconcile the apparent contradiction in part work. Finally, we propose strategies to access larger HTM read capacity, such as warming up caches and using huge pages. We hope these findings will help those of you building systems in HTM to make full use of it. Thank you.